here we have it, the fundamental theorem of calculus. Okay, so let's deal with part one. So first off, f is a continuous function. So here's my f, it's a continuous function. And then g is defined as the integral from a to x under f. So g is that area underneath the curve, anywhere from a to b. All right, so it's going to be continuous and differentiable. And look what happens. When I take the derivative of this, I get f of x. So let's just look at this. I'll prove this in class, but if I take the derivative of this special integral, it's a very special integral that's got an x up here, that I plug in the x into the function, and that's the answer. Okay, here we go. So take the derivative of this integral, very special with the x up here. So I'm going to plug the x in to the function, and so I get x to the fourth. Okay, this one has a little bit of a difference. The x is at the denominator, or the bottom limit of the limit of integration. So I'm going to carry this along, and I'm going to switch the limits of integration. And you remember that this is a property. When I switch the limits of integration, I have a negative outside. Now it's ready to go. So take the derivative of this very special integral with the x here. I get the carry the negative along, and I get 4 minus x squared. All right, ooh, looks like I have more than just an x here when I'm taking the derivative. Oh, that means I get to do chain rule. Okay, so I'm going to take the derivative and put the x cubed in for the t. So I get cosine of x cubed, and then I have to multiply by the derivative of the thing I carried along, so I get 3x squared. This has two things going on. I'm going to be taking the derivative of this, but I first have to put this in the top limit of the integration. So I'm going to say, okay, I'm going to take the derivative, put the negative out front, 2 to e to the x, carry this along. Now I'm going to do it. So I'm going to put in, or carry along the negative, I should say, substitute in the e to the x, so 4 plus e to the x, and then multiply by the function, the derivative of the function I carried along, so that's times e to the x. Okay, so I'll prove this in class also, but what this says is if I'm taking the area under the curve from a to b, it has to do with the antiderivative. And so I take this, means I put in the b first into the antiderivative, and then I subtract off plugging in the a. Okay, so let's first find the antiderivative. So antiderivative of x squared is x cubed over 3. The antiderivative of 5x is 5x squared over 2. So then we put this bracket here. And then what this means is now I'm going to plug in the 3. So plugging in the 3 here, so I get 27 over 3 plus, and I'm plugging in the 3 here, 5 times 9 over 2, and then if I had something to plug 0 into, I would have subtract off 0 minus 0. So this is the f of b, f of 3, and this is the f of 0. All right, so this gives me 9, right, plus 45 over 2, and I'm just going to leave it like that. All right, let's do another one here. So first I take the antiderivative of this. So x cubed over 3 plus 3x squared over 2. And then I'm going to evaluate it between 1 and 3. So first I plug the 3 in. So 27 over 3 plus, then I have 3 times a 9, so 27 over 2. Subtract off, now I'm plugging in 1. 1/3 plus 3 halves. And this is just going to be kind of ugly, isn't it? So I have 9 plus 27 over 2, and then minus, if I make common denominators here, of 6. So I would get 2 plus 6, right? No, 9. Oops. 2 plus 9. And 9 plus 27 over 2 minus 11 over 6. And I'm just going to leave it like that. So it's a number, which is the exact area under the curve.